This video is going to address the ControlLogix analog I/O modules. So the ControlLogix PLC comes on what's called the 1756 chassis. So all the various modules that you would purchase for the ControlLogix style PLC would be a 1756 prefix onto whatever module it is. And so these ControlLogix are fairly large PLCs, meaning that they can handle lots of I/O. So they come in, the chassis comes in various different sizes. The sizes can be as small as a 4-slot chassis all the way up to a 17-slot chassis. Now the chassis, when you start talking about the chassis and you start counting slots, the slots are always start counting by 0, not by 1. So in a 10-slot chassis, the last slot would be a 9-slot. Right. Now these modules are actually hot swappable, and they have a separate terminal block. So you can pull out the terminal block and then wire it up. So it's got like a little door on there. It'll pull off, and then you slide the door covering off, and then you have easy access to the terminals. And then you can wire up your terminals, slide on the door covering, and then press it back into the module. And the other advantage of this is that the modules are hot swappable, so if a module was to fail, you could just pull the terminal block off by opening up the door, and then it acts as a handle. You can just pull this section here right off, being careful not to pull loose any wires, and then you can depress on the top and bottom of the module and slide it out, slip in an identical module, and then just plug in the terminal connector. So it makes it very easy to do a replacement if one of the modules actually should fail. They also have other connectors to allow you a breakout so that you can have do your field wiring, so that you can purchase this connector cable that would just plug in there and then plug out to an expanded terminal for easier wiring. So it's just a picture of some of the various different wiring systems that are available. Our focus today is specifically on the analog modules. So we're going to talk about analog input modules and a little bit about the analog output modules. So if we're doing an input, we're going to take an analog signal, which we've already discussed. The analog signals can be either a voltage signal or a 0 to 20 kind of current signal. But whichever that is, we're going to bring that analog signal into our module, and that module then would convert and perform an analog to digital conversion, which a lot of times you'll see abbreviated as like ADC. And if we're going to send output, then we're going to take a digital value stored inside of the PLC, and that needs then converted into an analog voltage or current signal. So again, ADC indicates analog to digital converter. Okay. The ADC then is an input device or an input card, and the analog signal is going to be converted into a binary number. So now this is a number, it's not a bit, it's not a 1 or a 0, so it's a number. So typically it's going to be stored within a 16-bit memory location, right, which is a ward. So the analog converters that we actually have here in the classroom are 14-bit converters. Remember that the most significant bit of an integer is the sign bit. So a 0 indicates it's a positive value. 1 would indicate that that it's a negative value. Remember the 2's complement discussion. So if the most significant bit is a 1, that would indicate it's actually a negative value. And so it's a 14-bit converter, and we've got a 16-bit memory location. The most significant bit is the sign bit, and the way this converter actually works is it basically ignores the least significant bit. So it does a 14-bit conversion, but it's bits 2 through 14 or 15. It ignores the least significant bit, and then again the most significant bit is the sign bit. And if we're doing an output device, it's going to be a digital back to an analog. And again, it's a 16-bit memory location going out, and then that'll be converted then into either an analog voltage or current signal, depending on the type of module. All right, so let's take a look here at a circuit. This is a very simple 2-bit analog to digital input card. Okay, so this is only a 2-bit, so you have to multiply this times 7 to think about the complexity of the 14-bit analog converter circuitry that is inside of one of these analog modules. And this is just one channel, so this is just one input. So let's kind of take a look here and see how this works. So again, it's only a 2-bit analog card. So if it's only 2 bits, then that means that we can have either a 0, 0, I don't think my window's active here. Alright, so this is our 2-bit symmetrical. Okay, so this is a 2-bit symmetrical analog to digital converter circuit here. So 2-bit symmetrical. So that word symmetrical, that's kind of important here. So what we're looking here is we've got, in this circuit, we have this resistor divider network. Okay. So we have this resistor divider network, and that gives us our range of voltages to trigger a new value inside of our computer. So these LEDs over here, these actually were representing what would be the bits inside of that integer value stored inside the PLC. So we're going to have a bunch of 1s and 0s. So if the LED is on, then inside the PLC, that would be a 1 inside of that particular bit location for that input channel. Alright, so but notice this is symmetrical. What that means is that we have here, these are 2 kilo ohms here. It doesn't really matter that they're 2 kilo ohms, but what's important is that these are equal. Now if we were going to have a 14-bit, then we would have a lot more of these. So you would just have 2K, 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 and you'd have this huge chain of 2K resistors. Now on the top and the bottom, you would have 1K. Alright, so if these were 10Ks instead of 2Ks, then this top and bottom one would be half of that. So whatever it is, so it would be 5K. Alright, but it's got to be symmetrical because we're going to split these voltages up there. So that's the symmetric piece. Now these are operational amplifiers referred to as op amps, and in the mode that they are in, they are comparators. So we're basically doing comparisons. So if you see here, this line right here is at 5 volts coming in. This line is at 8.33 volts, and this line is at 1.67 volts. All right, and so these are the comparison lines. This little voltage symbol here indicates the voltage coming in from a sensor. So remember, this is an input card. We're converting an analog signal coming from some sort of external sensor and coming into our PLC. So we're going to convert it into a digital value. And so this is going to be representing, this signal is representing the sensor readings. So these sensor readings can vary. The sensor reading can vary anywhere from 0 to 10 volts. And this array of resistor, or this series connection of resistors here, is doing a voltage divider and giving us even breaks. Now we can go anywhere from 0 to 10 volts. So the max is going to be 10 volts and the minimum is going to be 0 volts. So this would be a voltage signal between 0 and 10 volts. And we have 2 bits. So 2 bits means So 2 bits means that we have 4 possibilities. We have 2 to the second power gives us 4 possibilities. All right, so those possibilities are 0, 0, 0, 1, 1, 0, and 1, 1. But if you notice, right, the 1 value here, the first value is 0. Right, so this that's the binary. Okay, so this is the binary. The decimal equivalent is 0, 1, 2, and 3. All right, so when you look at this, because we always have a value of 0, that's always going to be your first possibility. When you do your calculation, you actually have to take this maximum value and subtract 1. Right, so that your maximum is going to be a possibility of 3. So we're going to have 10 volts is the absolute maximum voltage we have, but 3 is the max number that we can get it with a 2-bit converter. And so we're going to have 3 minus 0. So we're going from the maximum possibility of 4 minus 1, or 3, to the minimum possibility, which of course is just 0. So then we end up getting our resolution of this now is a 3.3 volts, okay, per count. Okay, I just noticed up here it says bit. It's a bit count. Okay, so I just like to use the term count a lot of times because we're counting 0, 1, 2, 3. So for every new possibility of binary number, every time we add 1 to it, we've counted up 1. It's going to change. So now when we look at our signal, so again, this represents our sensor here, and our sensor can be outputting a voltage anywhere from 0 down here at ground all the way up to the 10 volt range. And so this signal can be varying, and it can just vary along here as long as it doesn't cross this threshold. Okay, as long as it doesn't cross this threshold, we just are sitting here at a value of 0. All right. So now notice that our resolution, this is our resolution, is 3.3 volts. And so when we step up, like if you look over here, we're at 1.67, and if we add to that 3.3, take it out to 2 decimal points, okay, 3.33 to 1.67, we're going to be at 5 volts. And then if we add to that 3.3, then we're going to get up to 8.33 volts. So our resolution, every time we change a bit, we're changing from 3.3 volts, except for the exception here is that this one is actually half of that, right? Because, and the reason for that, that's where this was a 1K and these are 2Ks. Okay. And then this is a 1K again. So we split the top and the bottom there. Okay. So we split the top and the bottom. Resistor values there. So we split the top and the bottom resistor values here by whatever value that the rest of the resistors are. So again, if we're doing a 14-bit converter, then you're going to have to add another 12 2K resistors in here between these two 1Ks. So basically for every bit you're going to have these 2Ks in here, but then on the outer edge you're going to have the 1Ks. And again, they don't have to be 2Ks, you just have to be consistent with whatever values that you're using so that you end up with this symmetric type of thing. But this first trip doesn't occur at the resolution of 3.3 volts. It actually occurs at half of that. So as the signal comes in here from 0, and once it crosses over this 1.67, then this input voltage here, which is being fed into here to this op amp, okay, as this comparator. So this comparator is comparing 1.67 with whatever our actual signal is. And if that's the case, this guy becomes a high, all right, which puts a 1 into this AND gate, which is going to give me a 1 over here. It's going to turn on LED2, or it's going to give me a 0, 1 output. So the second one, this LED, which is actually labeled LED1 in this circuit here, will still be a 0. So this will be a 0, but this one will go 1, and that'll turn this on, so we end up getting 0, 1 stored inside of our PLC. So once this input signal crosses this threshold of 1.67 volts, then we're at 0, 1. And this thing can sit here and wander around up and down, and as long as it's between these two values here, then our input is going to be reading a 0, 1 into the PLC, or in this circuit we're going to have a 0 and 1 on these LEDs. Alright, so now once the signal, if the signal actually drops back below this again, then the signal would then go back. Anytime it's below that threshold, it would be feeding 0, 0, or the LEDs would be off in this. But if the signal continues growing, and once it crosses this 5.0 threshold, so the signal here gets above that, now we're going to turn this op amp on, and then it's going to turn this light on here on this LED, or we'll have a 1, but the second LED would return to a 0, so we get a 1, 0. All right. And so again, as this thing, it can bounce around here all at once as long as it doesn't drop below the 5 volts and or cross the 8.33 volts, then we're outputting a 1, 0. Once it crosses the 8.33 threshold, we're going to get a 1, 1. Okay? So a 0 reading inside the PLC, a 0 reading means that the sensor is outputting somewhere between 0 to 1.67 volts. Okay. And again, that 1.67 volts, technically it's 1.6666, okay, and this just goes on indefinitely. All right, so once we cross this threshold, then we're going to have, so if we're at 1.67 volts, or actually 66667, if there's a 7 pops up in there anywhere, we're across that threshold, and so so this is our voltage here. So 1.67 up to 5.0 volts. All right. Once we cross this 5 volts, then we're going to be at a 1, 0. Okay. So if we're at like 5.0000000000000001 here, once we cross that, then we're at 1, 0 until we get up to 8.33333. And then once we cross 8.3, so we get to something like 8.34, all the way up to a possibility of 10 volt, we're outputting the highest value of 3. All right. So again, this is a simple 2-bit converter. This could be easily expanded to a 8-bit converter, 12-bit converter, 14-bit converter, but the circuit is going to get much more complex, right? So every time you add one more bit, you're doubling the complexity of this circuit. So if you do a 14-bit, this circuit is very, very complex, but the way it works is pretty much identical to the way this 2-bit converter works. All right, so given that, all right, that's the analog to digital converter. So this slide just kind of breaks that out there. So the max value again is your 2 to the power of your bit. So if it's a 2-bit converter, it's 2 to the second power minus 1, so your maximum value is 3, because again we always start counting from 0. So the resolution is going to be your maximum voltage divided by the maximum digital value you can get. So we had like 10 volts divided by the 3, which gave us a 3.3 was our resolution. The actual force voltage detected is going to be half of that. All right, so the sensor could be anything. It could be a thermocouple measuring temperature. It could be a load cell measuring force. It could be some kind of frequency detector. Any kind of sensor can output a voltage between 0 to 10 volts. One thing I do want to mention here, if your voltage, one of the voltage signals that is a valid voltage signal is -10 to +10. So if that's the case, then your voltage range, you would actually have to use like your voltage range here. I should maybe say voltage range. Okay. And so that voltage range would be from -10 to +10, so the voltage range would actually be 20. So you would have to account for that in there. All right, So this is just kind of a slide showing you the various different possibilities. Again, the 1756 is the ControlLogix. We also have in the classroom the compact logic modules. All right, but this is just kind of listing some of the possibilities for analog input modules. All right. Here's kind of a close-up of a compact logic module. And actually what you'll see, like in the classroom, when we look at various different modules, like our relay module is a good example. Our relay module is an OW16 in the ControlLogix PLC, and it's an OW16 in the ControlLogix and in the compact logic. So, but what changes is the chassis number. So for our So for the ControlLogix, the relay module, now relay modules of course are digital, but the relay module is a 1756-OW16. So it's a 1756 OW16 for the ControlLogix, but for the compact Logix you would buy a 1769-OW16. So they're essentially the exact same relay module. They're just their structure is slightly different, whether you're going to plug it into a 1756 chassis or plug it into the 1769 compact chassis. So your analog input module, depending on what they are, but a lot of your input modules can actually handle either a current in or a voltage in. So it depends on the exact analog module that you have, but a lot of input modules can do either voltage or current. All right, you can purchase a card that only does an 8-bit conversion, which would give you 2 to the 8 minus 1. Okay, or you can buy a 12-bit, which would be 2 to the 12th minus 1. Or you can buy a 16-bit or 14-bit or whatever, okay? And these would be your maximum numbers, okay? So remember, it's 2 to the number of bits, but then the max value is 1 minus that. So the maximum number is 255. 2 to the 8th is 256. 2 to the 12th is 4095. Now the 16 bit here, you got to be careful, because remember, you're storing this in a word which is 16 bits, and that most significant bit is actually going to be a sign bit. So you kind of have to be careful there. Okay? But each count represents a bit change. So if we flip back over here, right, we had 0, 0, 0, 1, 1, 0, 1, 1. So each count was a bit change, and that bit change represented it crossing the threshold on the individual comparator. So like here we got a 2-bit comparator, and so we actually had 3 comparators in here to get the possibility of 3, right? That was our maximum number over here, was 3. And so the comparator, if our maximum number is going to be higher than that, we're going to need a lot more comparators if we have, an 8-bit or a 14-bit card. All right, so this is just kind of showing some of the different modules. This one over here in the bottom left is actually a PLC5 module. But we're using like the ControlLogix module. So the ControlLogix modules, again, you can buy some 16-bit ones. They get really, really complex. The one that we have is fairly complex. It's a 14-bit module. Alright, so when you wire this up, like one card can have multiple different channels, so it's actually going to have multiple of those analog to digital converters. Every channel has got to have its own analog to digital converter. Right? And so you're going to have multiple channels in here. Now, one thing to keep in mind, most sensors actually output a 4 to 20 milliamp signal if they're a current analog current signal, but the I/O module, the analog to digital module inside the PLC always converts from 0. All right, so we're always converting from 0, even though we may be receiving a signal that never drops below 4 milliamps, assuming that it's a good signal, valid signal. But the analog input card is designed and always reading from 0 to 20 milliamps. So when we do our calculations for our resolution, we're always using 20 milliamps, not 16 milliamps. So as I mentioned earlier, the Allen Bradley PLCs use a 250 ohm. Actually, if you look at the documentation, it's actually a 249 ohm resistor there. But that means, like, if you're feeding it a current signal that's going to range anywhere from 0 to 20 milliamps, 20 milliamps times 250 ohms is going to give you basically a 5-volt drop. So remember, this A to D converter circuit here, this A to D converter circuit is actually a voltage. It's measuring the voltage. It's using these voltage thresholds over here. But so a current signal is coming in, it's being dropped across a 250, we'll just kind of round up for simplicity, call it 250 ohm resistor. Therefore, the voltage range in that case is going to be a 5-volt voltage range instead of a 10-volt. So the example I did was with a 10-volt voltage range, but if you're feeding in a current signal, it's the same idea, but your maximum voltage would only be 5 volts. So when you do your comparison, if you look at that comparator here, this here, our voltage feeding this resistor range was 10 volts. So all you have to do is change this to a 5 volt, and the rest of the circuit would be completely unchanged. So you just change your supply voltage for a 5 volt. And so that's kind of like the major difference there, whether you're doing voltage or current. All right, now when you start wiring these up, like the ControlLogix card that we have actually has 16 input channels. However, when you wire them up, you can wire them in what's called differential mode or single-ended mode. If you do differential mode, you actually end up dropping down from 16 possible input channels down to 8. Okay, but if you do single-ended mode, that means that they all have a common ground and that you can actually have all 16. So here's some information out of the manual for the ControlLogix IF16 input card. Also the IF8. So the IF8 module only had 8 analog input channels. The IF16 has 16. So they usually, the numbers match. They're telling you how many channels you have. But if you tie all the inputs to the same common ground, then you can use all 16 channels in the IF16 card. So you got 16 analog input channels. However, if for whatever reason you need a separate ground, if you need a separate ground, then what happens is you end up losing half your channels. All right, but the advantage is that the channels that you are using all can have separate grounds. All right, so this shows the wiring. On the left, it shows you differential wiring. So notice there's this I return 0 here. The I return 0 gets fed back over into the IN1. if you're using differential wiring, you have to put this little jumper in here. So by putting that little jumper in there, you're using your IN1 channel. So you're only getting half as many channels. So you're going to have channel 0 up through channel 7. However, if you do single-ended, which is on the next slide, so if you do single-ended wiring as shown over here, your returns are all you jumper your return, because remember, we're talking about current here. This is for current wiring, and when you do current wiring, you got to have a return. So that's what these returns are for, because you got to have a complete circuit. And so you got to feed this current in, the current's got to come in, and then it's got to be able to return back to the sensor. And so that's why there's all these return connections here. So if we do single-ended, we just have that return, and they all run through a common ground. So all the sensors have to be wired up to a common ground. But if you're using the differential mode, so if we get back to the differential mode, so if we look at the differential mode, right, we're jumpering that return, then is feeding back into the IN1, and we have individual grounds. So each one of these sensors has its own ground and return. So we're going in, the current is going into IN0, okay, and it comes out the return, back out IN1, back into your sensor, because we need a complete circuit for that wiring. Alright, so I already kind of discussed that this can be removed. Any of these modules can be removed under power. But what this circuit is showing you here is the wiring for an output module. Now, as we said, the input modules have a 250 ohm resistor inside of them. And in general, when you're doing current and you're feeding connections, you can, you're going to be feeding probably a 250 ohm. That's a pretty standard resistance. But remember, we talked about when you're doing current, one of the advantages of current signals was you can daisy chain them again. So if you're going to feed this out to a 250 ohm resistor, you would wire it out through out 0. This is for the analog output module. So the analog output module, you have your output current is going to come out, and then it's going to go into that device and come back into the return 0. Alright, and you could daisy chain this, because you could, if this analog output device was 250 ohms, this wiring here shown is good up to 500 ohms. So you could actually wire in yet a second one of these devices. Alright, so this here is showing then two devices daisy chained. So if each one of these was just 250 ohms, then we could wire up and feed into the first device, come out of the second device, and daisy chain into the second device, and then come out of the second device, and then we could still go into that return 0. However, if we were going to daisy chain a third or a fourth device all the way up to 1,000 ohms, we would have to change this return wire into the alt 0. Alright, so slightly different wiring for anything more than 551 ohms. Notice the slide says 551 down in the below there, but the red text was saying 0, so that was actually incorrect there. Let me move this up here a little bit. Alright, So for loads of 551 to 1,000 ohms, you actually need to wire it through the alt connection. So if you're daisy chaining it. Now, if you're outputting, let's go. I'm going to scroll here to the end of the slides a minute. Let's look at the scan times of a PLC. So if you remember from PLC 1, we talked about how the PLC actually executes a program. So the first thing it does is it reads all the inputs. So it goes through and it reads all those inputs and stores those values into their dedicated locations within the PLC memory. And then it executes the program. It's executing the program based on those values that read. So while it's executing the program, those values aren't changing. The values may actually be changing out in the real world, but as this scan of the execution of the program inside the PLC is being executed, those values are essentially held constant as far as all the ladder logic goes, because it only reads those input values once during the read input phase, and then those values inside the PLC are not changed again until we make it all the way around the scan loop. So during the calculations within the program, these inputs are considered constant. Now remember, a scan is probably only maybe a few milliseconds or something, so a full scan is fairly quick. So unless the outside, the actual value from the sensor is changing a whole lot, it's not going to affect too much, because a scan occurs fairly quickly. But also remember that the scan can slow down as the program gets more complicated. The scan slows down as you add more inputs to read. This section, the read inputs, is going to take a little bit longer to read all the different inputs and store them into their locations within memory. And likewise, when you're setting your outputs, the more outputs you got to change, the longer this section is going to take. So the scan time can get longer and longer as the program gets more complex. But in general, the inputs, once they're read and then you begin the execution of the program, they're constant for that one scan of the program code. And then the program code is calculating what the outputs are going to be, and then after it's calculated all the outputs for everything in that code, in that scan, then it sets those outputs. And so those outputs stay set, and then it to whatever value that it calculated, then it goes through the process again. It reads in any changes to those inputs. Then it goes through and it totally executes the code again. And while it's executing this code, however long that takes, whether it's 1 millisecond or 2 milliseconds or 15 milliseconds, however long, depending on the speed of your PLC and the complexity of the program, the output values have not changed. And so until the execution of the code is done and it's run through its diagnostic communication phase, and then the outputs are updated. All right. So what that means is that if we have an analog output card, let's say that we wanted to output this nice pretty red sine wave. So the red is a ideal sine wave that we're sending out, where the voltage is stepping up from 0 all the way up to 10 volts. So that's what we want to put out, from a 0 to a max of 10 volts, and then down to a negative 10 volts. So this is assuming that we're going to have this plot here is assuming we actually have a minus 10 volt signal to a plus 10 volt signal that we want to output. So we want to output a nice pretty sine wave like this. Well, what turns out is, number one, what we get is the blue step ladder sort of output. because we're only outputting a new value at a new scan, at the end of a new scan, right? And so we get these steps because we won't get a perfectly nice, smooth wave. It's actually going to have steps in it. Now, again, the time scale on here is actually showing seconds. So if we're doing milliseconds, you may not hardly notice it. It may look almost like that perfect thing. But the other thing is, notice up here at 10 volts, we're not going to make 10 volts. It's actually going to be, 8.33 volts or whatever. So let's look at the circuitry for a digital out. So a digital out looks kind of like this. Notice here we have 8, 4, 2, and 1. So if you remember when we were doing binary conversion, alright, so if you're doing binary conversions, remember how we have like the 1's column, the 2's column, the 4's column, and the 8 column, right? We get the same sort of thing going on here. We have a 1, 2, 4, and 8. Now the only catch here is that this one is actually your 1's column, because notice there's 8K there and then there's 8K over here. So what you're doing is you're kind of doing a comparison between this 8K resistor R5 and whatever resistor this is. So you get 8K divided by 8K is the 1's column. So if you turn on switch 4, then that's going to make the 1's column active, right? So if I had this binary number 0, 1, 0, 1, okay, so that's my binary number, which is a value of 5, okay, but that's going to generate my output voltage. So now in this case I actually have 1 volt out, but you would do that for whatever, and then you would amplify that voltage. But when we look at this as we close these switches, notice this voltage is wired in here backwards, where the positive is actually connected to the ground. The reason for that is because this op amp, we're feeding it into the negative. Okay, so we're actually feeding it into the negative, so it's actually going to invert the voltage. So we're kind of putting in a negative voltage so we get a positive voltage out. So if we take this, we would put a 0, 1, 0, 1, right? 0 means that the switch is open, and a 1 means the switch is closed. So we would close switch 2 and we would close switch 4, and that would give us, take this binary number, which is decimal 5, right? 101 is 5, and that would output that 5 through our amp and give us a fixed voltage out, and that voltage would stay that way until the next scan time. But this is how this is a simplified circuit here, but this is a digital to analog circuit, and so the equation for that comes here. So you have these switches divided by your resistor values. So you basically have like R1, you have this reference value here, so then you have 1 divided by R1, okay, which would give you 8. So if you had a 1 over here, that would give you 8. So basically what we're saying here is you would have either a 1 or an 8 here, and remember this is an 8, so this is 8, but then this is a 1, or 8K actually, and this one is a 1, so we're dividing by our 1. So we have an 8K divided by 1K, which gives us an 8. So if S1 is a 1, that gives us 8. But in our case, S1 is a 0, but S2 is a 1. So that gives us over here, we get a 1 divided by 4 here. 1 divided by 2K. Okay. So we have this, again, there's 8K here. So this 8K, let me put it, so 8 kiloohms. This is a RF, this is RF, R5 in this case, okay, is the 8 kiloohms. So you got the 8 kiloohms, and then if you're doing switch 2, that's R2, and R2 is 2K. So you would have 8 divided by 2, which of course gives you the number 4. So you would have 4 plus, and then you have a 1 here. So you have 8 divided by the 1K over here, which would give you a 1. And so that would give you 5. So your voltage out would be 5. Your voltage out would be 5 divided by your voltage in here. So voltage out, so you'd have that. So to get the maximum voltage of 1 volt, you would have to have this to be all 1s. All right, but instead we're actually getting a portion of that out. I'm sorry, this switch was an 8K here. This was an 8K. All right, so if you stick that in, that's going to be what your voltage is. Now again, this simple circuit was assuming a 1 volt value, so the max that we could possibly get out would be 1 volt out. However, we won't actually get that 1 volt out. Okay, so it would actually be slightly less than that depending on our resolution. So we're never going to get that maximum. This section right here, you're never going to get above the 1111. Okay, that value is actually kind of cut off right here, but this line here is all 1s. So this line right here is all 1s, and you're never going to get above all 1s, but that all 1s, is this dotted line. So this bit, you never actually reach this bit here. Okay? You never actually reach that bit. You do, however, if you're going all the way down to negative 10 volts, you could possibly actually reach negative 10. So, because when you look at your lowest value, you can actually reach, okay, because that's the possibility where you're all zeros. All right, so in this circuit that I had up here, this one doesn't go negative, so the minimum that you can possibly get out of this circuit here is all zeros. So you could either have 0, 0, 0, 0, or you could have all 1s. So the max bit is going to be less than this maximum value. You're never going to get that maximum value.